Hi everyone. We're going to change things up now, leaving metallic systems behind. Over the next two lectures, we're going to cover polymers. In this part, I'll go over some of the basics of what makes up a polymer, and then in the following lectures reference these basics when describing their behavior. Engineering polymers, as opposed to natural ones like ivory, tusks, and silk, have been around for at least 150 years. Parkezine was invented as a substitute for ivory billiard balls, and Hyatt's celluloid replaced it. Celluloid, which is some of the earliest movies were recorded on, turned out to be pretty volatile stuff. Apparently, if you hit the balls just right with enough force, they would explode. While in some circles, this would make the game a sight more entertaining to watch. This is one of the many reasons which drove the development of fully synthetic polymers. This kicked into high gear during the middle of the 20th century, driven by the need for cost-effective, rapid production of many consumer goods. Now, we're surrounded by them, and they're not going away anytime soon. A good a place as any is to start first with defining what a polymer is. Often the term is used interchangeably with plastics, which can confuse things. The strict definition of a polymer doesn't really help from an etymology perspective. The word polymer is derived from two Greek roots. It literally means many parts. Therefore, a polymer is something that's made up of many parts. Often, synthetic polymers are referred to as plastics, but that is more of a descriptor of their behavior instead of their nature. The reason why they are often referred to as plastics is because they are pliable and easily shaped, like when a metal is made to go plastic. So the word plastic really should be used as an adjective to describe the way a material deforms under a load. It just so happens that polymers readily exhibit this quality. The definition of a polymer is generally described as long chains of hydrocarbons, molecules that are comprised of hydrogen and carbon covalently bonded together. Now let's look at how this collection of many parts of hydrocarbons form to do just that. Let's start first with an example of how a single part, a monomer, becomes a polymer. As an example, ethylene, which looks like this on the left, can undergo a polymerization reaction to turn into polyethylene. Carbon has 4 electrons that can participate in covalent bonding, and hydrogen has only 1. The double bond can form a single bond, allowing multiple ethylene molecules to bond with others. In this reaction, multiple monomers of ethylene can join together to form a polymer with very different properties. Ethylene is a gas, while polyethylene is a solid. The polymerization reaction doesn't happen spontaneously. Under carefully controlled temperature and pressures, along with a catalyst, then the chain can start being created additively. I've shown the catalyst here with an R dot, and when it sees a monomer, then a polymer will grow from the active site at the end. That is, the catalyst will break the double bond of the monomer, so there's an active site to break the double bond of another monomer. The arrangement that continues looks something like this, and demonstrates a mer, the part that is repeated many, many times over to form our polymer. It also demonstrates the distinction between a monomer and a mer. A monomer is the stable form of the mer. As with other chemical reactions, this process carries on for as long as conditions favor. Let's now look at what physical structure presents itself of these chains of polymers. The reality is that angles between carbon-carbon bonds in polymers is not 180 degrees as depicted previously, but closer to 109 at any orientation. Say that the short polymer is the polyethylene shown before. This means that the last mer can occupy a space anywhere on the black dashed line. If this carries on for a longer and longer chain, then the characteristic zigzag of each hydrocarbon mer can be shown. In 3D, the only constraint on the location of each mer relative to each other is that the angles between the carbon-carbon bond is 109 degrees. As a result, a long polymer chain can demonstrate many coils and kinks which are made permissible by chain bond rotations. Without structure, a large number of these chains massed together will resemble a mass of loose string or yarn, each individual chain of neighboring chain molecules, a plate of spaghetti. The orientation is random, the degree of intertwining is random, as there is a high number of degrees of freedom of each individual chain. There are many different types of polymers, some of which you've heard of before. For example, there's PTFE, polytetrafluoroethylene, known more commonly under the trade name Teflon. The mer for PTFE is comprised of carbon-carbon and carbon-fluorine, which is used over a wide number of industries because of how stable it is. Compare the electronegativity of fluorine versus hydrogen, for example. Another one is PVC, polyvinyl chloride, a relatively high-strength polymer that's used in the construction industry. Further, there is polypropylene, which is widely used in the food industry. Its mer has an additional short-chain hydrocarbon, which can participate in further tangling up with other chains. However, the backbone for almost all polymers is the carbon-carbon bond, and the number of these, and therefore the overall chain length, can decide properties. Specifically, the number of carbon-carbon bonds decides the properties of both polymers and hydrocarbons. For example, ethane, involving 2 carbon-carbon bonds, is a gas. Butane, adding another 2 carbon-carbon bonds, is a liquid. Adding another 10 to 40 carbon-carbon bonds, we end up at paraffin, a wax. Adding an order of magnitude more carbon-carbon bonds, then we start arriving at the properties of some plastics that we're familiar with, at least at room temperature. Polymer chemists have a term for this, molecular weight. This isn't necessarily the best descriptor, as it's the mass that increases with chain length, but molecular weight is a term which is employed extensively in the polymer industry. The higher the molecular weight, the more properties tend to be more solid. And it has a role on other properties too, which will be described shortly. The structure of our polymers, condensed, can take on 3 different conformations. The simplest are the linear variety, linear in terms of how the mers are arranged, not how they collectively behave. Our first example of polyethylene is characteristic of a linear polymer. There is also cross-linked or network polymers, where there are primary bonds between the chains, and this will be covered in much greater detail in the second part of this lecture. Further, there are branched polymers, an example of which is polypropylene as described earlier. All these types of polymers have very different numbers of entanglements, regions which are intertwined with other chains. In the case of cross-linked or network polymers, there is a physical primary bond which links different chains together. But for all, there are secondary forces acting between the chains, which leads to a greater number of potential sites where chains can tangle up. So, beyond the specific examples of polymers already described, how can these varying types of arrangements be attained, or more broadly, different properties potentially attained? The answer is copolymerization. The definition thereof is to purposefully add different mers to achieve different response from the underlying polymer. These differing mers can be added on the basis of 4 routes: randomly, on an alternating basis, in blocks, or by grafting as shown here. The mechanism for doing so is down to the nature of the mers involved and underlying chemistry, but here are 4 examples: synthetic rubber, SAN, used in a wide range of consumer goods; PMMA, known more widely by the trade name Perspex or plexiglass; and finally, high-impact polystyrene, used in the medical and food industry. There are more important examples of copolymerization that you'll likely encounter in your careers if you haven't already. ABS plastic, for example, nylon, and PEEK. The takeaway here is that copolymerization is one route to get functionalization, analogous to alloying in metallic systems. Combining multiple mers allows one to arrive at properties that would not otherwise be attainable with a mer of a single type. So in this part of the lecture, the basic nature of a polymer has been described. A very long molecule which is chemically created by the sequential bonding of mers to form chains. These chains have a fairly high number of potential conformations or ways in which they can manifest. Unorganized, they behave analogous to a collection of loose string or a plate of spaghetti. Generally speaking, the longer a chain of hydrocarbons is, the higher the molecular weight and the more the result will behave like a solid. The higher the molecular weight, the more opportunities that they have to take on different configurations in terms of interaction between chains, and copolymerization adds to the flexibility that this type of interaction can be attained. Until next time.